Hey, it's Dr. Jake. Part 3 of 5.1. I know I've gotten in a bad habit of doing these 3-part videos, but this is very important. Third part. Today we're going to focus solely on applications of quadratic functions. Now there are hundreds, if not thousands, perhaps even millions of different uses or applications of a quadratic function. In this course, I'm really going to focus on 3 main types. We're going to talk about geometry applications, in particular rectangles. Although there are other geometric properties and applications and word problems, if you want to call them that involve other shapes, but I'm just going to limit it to rectangles. Oh, that also includes squares, by the way. A square is a special type of rectangle. We're going to talk a little bit about projectiles. What's called projectile motion. In other words, an object moving through space, flying or falling, thrown, whatever, launched. Although I probably shouldn't use the word flying. I mean, it is flying, but it's more like, you know, the way Buzz Lightyear flies in Toy Story. You know, he's actually just falling the whole time. If you're actually flying, it's actually quite a different formula. This would be, you know, falling with style as opposed to actually flying. So a falling object, a thrown object like a baseball or a football or a rocket, you know, it's being launched in space and something like that. Okay, enough with that. And then the third application will be business math or money problems. Yeah, we all got money problems. And I can't necessarily solve your money problems any more than I can solve my money problems, but I can certainly solve some business math problems. And then in the business math problems, we are going to review some of the formulas from section 4.1, which hopefully you've recently watched. Maybe you watched it last week. I don't know. Maybe you just watched it yesterday. I don't know. But if not, if you haven't watched that one in a while, I would go back and review some of the formulas from 4.1. All right. So that's a brief summary of what we'll be doing for the next hour or so. Let's just get right at it. We'll start with geometry. I hope it's obvious why geometry is a good application for a quadratic function. It might not be obvious, but when we talk about geometry, x squared is the area of a square with each side equal to x. So, I mean, it makes perfect sense that the reason why we call it x squared is because it relates to the area of a square. So, you know, if I have x on each side, so if this side is length x and this side is also length x, then the area is x squared. It's the inside of the square. Sometimes called x by x. Yeah. Area is x by x, or x times x, which is x squared. And then for a rectangle, if you had something like this, where this side is x plus 1 and this side is x plus 3. Now again, a square is a special rectangle. A square is a rectangle in which the sides are the same. This is what we call an honest rectangle. Yeah, the sides are not the same. Yeah, it's a true rectangle. or you could say it's a non-square rectangle. The area would be x plus 1 times x plus 3 again. Now again, I don't label all 4 sides of a rectangle. I only label 2 of the sides, the length and the width. I think you can use your imagination. If this side is x plus 3, then this side is also x plus 3, and vice versa. If this side is x plus 1, then this side is also x plus 1. So I'll only be labeling 2 of the 3 sides. Okay, and then the area would be x squared plus 4x plus 3. So you can see how these are quadratic functions and how they relate to the area of a rectangle or a square. Let's do an example. So our main goal in this geometric interpretation of quadratics is not to graph them or anything like that. I mean, if it becomes necessary, I'll draw a graph, like maybe when we get into some of the more advanced problems. But for some of these, elementary, example 1, example 2 kind of problems, we're really just going to be solving, right? Just setting up an equation and solving it, and then hopefully relating it to something in the real world. Let's start off relatively abstract. We have a rectangle such that the length is 4 inches more than or longer than the width. If the area is 60 square inches, what is the length and the width? I can say it very quickly. I can say, what are the dimensions? So just a quick vocabulary reference. Dimensions is asking for the length and the width. All right. Okay, so maybe I'll kind of go through the word problem technique really quick. Word problem, also known as apps or applications. Technique. R, read. Yeah. Draw. D, draw. Translate. Solve. And then check. This is sometimes called the 5-step method. Read, draw, translate, solve, and check. Sometimes we skip drawing, but I'm not going to this time. It's geometry, right? But I mean, if the problem has no geometric interpretation, if you can't really visualize what's going on, we sometimes will skip drawing and go straight to translating. But whenever possible, draw a picture. So read it. All right. Now this is how we read mathematics. We read critically. Okay. Length. So I've got L. Yeah. Is equals 4 more than, longer than. So 4 plus width, W. Okay. Area, A, is equals 60. 60. I don't need to write that twice. Okay. I'm not really going to worry too much about the inches and things like that. I could be really mean and give you like one problem with inches and another thing with meters and then have you convert between inches and meters, and that's a different class, all right? I make my beginning math class do that. Believe it or not, they kind of have a harder time with these problems because I really throw out lots of different units like feet and yards and miles and inches. I'm not going to do that to you, all right? Because I'm much more concerned with the technique and solving the problem. I don't want to throw a wrench in the engine. So the main thing that I will point out about the units is that length and width are what are called linear. So they're just what we call regular inches. And then area is square inches. And then if we go into the third dimension, like a box, that would be cubic inches. And that's about all I'm going to say about that. So basically, when you're translating, you can just sort of ignore the units to the extent that they're not going to affect how you solve the problem. They might affect how you answer. So you'll say, you know, the length is 5 inches. So, I mean, they're going to affect your final answer, but they're not going to affect the technique. All right. So I don't really want to get into that right now. All right, good. We read it. You can read it several times if necessary. You know, go back and read as you're drawing. So now let's draw a picture. So we got a picture here. We got A is the inside. We got L. We got W. You don't need to label all 4 sides unless you really want to. Just pick 2 of them. Now, you don't want to do something like this. You know, that wouldn't make any sense, right? Because if this is L, well, then that also has to be L, and vice versa. If this is W, then this also has to be W. So label 2 distinct sides. All right. What does it say? It says the length is 4 plus W. So when I translate, drawing and translating are very similar. They're sort of related. I'm drawing the picture and I'm translating. And then A is 60. Okay? Now, I got to do a little bit more translating. I've got A is L times W. Area is length times width. And now I want to plug everybody in. A is going to be 60. L is going to be 4 plus W. And W is just going to be W. I'm not changing W. Okay. Hint. The translation should have only 1 letter. I don't know if you guys have probably noticed, but my face used to be over here. My head, which is now over here, used to be over here. I realized that I was writing right over my head a lot, so I've now moved my head to the left side. And I don't know, sometimes you'll watch videos that were filmed, you know, a couple months ago or something, and my head might move back and forth. It took me a while to get good at this and not write right on top of where my face is. So, anyway, that's my little disclaimer, so how my head moved. Oh, and I seem to have lost my hat today. Okay, so if you've translated this correctly, then you're ready to solve. So make sure your translation is all correct. Read it a couple times. Make sure it's simplified. There's a couple things you can do. You can change the order. This eraser needs to be retired. You can change the order. I like to put the 60 on the right-hand side. It just makes it a little bit more friendly to my eyes. I don't really need the dot because I have the parentheses. I should probably get rid of the parentheses. Oh, there's that. Okay, and I should probably put this in the standard form. Okay, and so this is what you want to solve. And you have 3 methods that you can use. You can use factoring. You have to set to 0 first. You can use the quadratic formula. which you also have to set to 0 first. Or you can use completing the square. I only do that. I do not set to 0. So for completing the square, I do not set it to 0. And I look at the middle term. To decide if it will be easy. Remember, I mentioned this in maybe it was the first or the second part of this lesson. I can't remember. It's one of the two. I might have mentioned it both times. If the middle term is even, then this is going to be easy. Yeah? I'm definitely going to complete the square with this one. Okay. Okay, so what's half of 4 squared? Yeah. Half of 4 is 2. 2 squared is 4. So I'm going to add this to both sides. So I'm going to get w squared plus 4w equals 60. And I'm going to add plus 4 to both sides. So now I've got w plus 2. W plus 2 equals 64. Or w plus 2 squared equals 64. Now, if you don't like this method, you're not required to do it. You could just use ordinary factoring, or you could use the quadratic formula. Either one will work. I like completing the square, unless the middle term is odd, and then I pretty much avoid it. Okay, now we're going to square root both sides. Now, here's the cool thing about completing the square. In geometry, there's no negative numbers. All right, no negative numbers. I'll just write no negatives. Yeah. So that means I really, even though I have plus or minus 8, yeah, there are 2 possibilities, I can't really have negative 8. It wouldn't make any sense. Yeah, negative 8 would not make any sense at all. So when you factor, you sometimes get negative and positive answers. Same thing with the quadratic formula. But completing the square, as long as I remember, I'm doing a geometry problem. So geometry doesn't have negative numbers. Think about why, right? Geometry is about measurement, right? It's old school. It's thinking about like if you were living on Earth 10,000 years ago. You didn't know what negative numbers were, but you could still measure a line. Yeah, you could still draw a square in the dirt. All right, but there's no negative numbers. They don't exist. They haven't even been invented yet. So when I go to solve this, one of the reasons why I use positive completing the square is because there's only the positive result. So we're going to subtract 2 from both sides, and we're going to get w is 10. I don't have to worry about the 2 possible answers unless both possible answers were positive. Typically, when you do this process, you end up with 1 negative and 1 positive, and so you can automatically toss out the negative. Now, I should mention, if both of these came out to be positive for some miraculous reason, it could happen, 1 in a million chance that it could happen. It really has to do with how big the number on the other side is. I'm not going to purposely make up a miraculous answer, but I mean, if both of them came out positive, you would get 2 possible answers. That's not going to happen on the test. Okay? So it's just going to be the one of them's negative, one of them's positive. There are no negatives allowed, so you can just ignore the negative and just give me the positive answer. Okay? Now go back, read the question again. It says the length is 4 more than the width. Or maybe it said longer. I don't know. It doesn't matter. More than, longer, same thing. So therefore, length is 10 plus 4, which is 14. So the dimensions are somebody almost got extra credit. 8 minus 2 is 6. I knew one of the numbers was 10. It's just the length is 10, the width is 6. That was close. So there's your dimensions. All right. Almost blew it. I almost went 10 minus 2, and I almost wrote 8 minus 2 and put 10. Yeah. It goes to show that human beings are human beings, no matter what. Yeah. Everybody poops. Yeah. And I just almost screwed that one up. Okay. Checking. I'm just going to do a mental check. All right, mental check. Because I don't really expect you to go back and, I mean, if you do an actual check, you might as well just solve the whole problem all over again, right? Let's just do a make sense check. We call this a sensibility meter, yeah? Does it make sense? Yeah? So let's do a check, okay? It said that the area is 60, yeah? Does that make sense that the area is 60? There's two things you want to check. You want to check the area, and you want to check the 4 more than or 4 longer than. Does it make sense that the area is 60? Yes, it does. 6 times 10 is equal to 60. Yes. Yeah, that checks. Yeah. And then finally, is the length 4 meters longer than the width? Is 10 equal to 6 plus 4? By the way, the mistake that I just made, if I would have left it a mistake, I would have caught it right here. Right? I would have gone, wait a minute, the area was not coming out to be 60. Or one of the other things is sometimes the length and the width are not 4 more. But yes, that one also checks out. So just give it a quick second or 2 seconds or 10 seconds, and it'll save you maybe even an entire semester if you just check your answers. Okay. All right, that one's done. Next example. Example 2. Talk about perimeter. The perimeter of a rectangle is 36 centimeters. And the area is 72 square centimeters. Centimeters squared is the same as square centimeters. We usually read it backwards. Square centimeters. What are the dimensions? Okay, so now we have 2 different things going on. Let me just do my read, draw, translate, solve, check. This is just to remind me of my technique. All right, perimeter. Perimeter means perimeter. Peri means outer, meter means measure. So that's the outer measure. That's literal translation of perimeter, outer measure. So you have a rectangle You have an L and a W. And you've got the perimeter is 2W plus 2L. When I'm talking about perimeter, I like to draw all four sides because for perimeter, it's kind of important. You have two L's. That's two L's. You could also just say L plus L. Means the same thing. And you have two W's, which you could also say W plus W. Okay. And then I have area. So I know that one's 36, sorry. So that's my P. So notice I read and draw kind of simultaneously. So that's going to be 36. All right. I'm reading and drawing simultaneously. I'll put that inside so it doesn't mess everything up. Maybe this one too. We'll put them all inside if we want. It'll give us a lot more room to work. There we go. And this is just for reference anyway. Notice I'm not really using the rectangle to solve the problem. It's just to make sure that what I'm doing makes sense. Okay. And then I have the area is 72. So A is 72. Which means that length times width is 72. All right. I don't want to have a variable called A. So as soon as I see the variable A, I immediately replace it with length times width. Same thing with P. I don't want to have a variable called P. All right. Remember the hint was to make sure that there's only one variable. So P becomes 36 immediately. Okay, so now we're going to translate. You're kind of translating while you're drawing and while you're reading. So it's kind of read, draw, translate, read again, draw again, translate. So these three things are kind of all kind of moving around in different orders and going back and forth. And don't start solving until you have resolved the RDT, the read, draw, translate. Make sure you've got it all figured out. One thing I like to do is I like to calculate what's called the semi-perimeter. It just means that you take the perimeter and divide it by 2. And when I say divide it by 2, I literally mean divide everything by 2. We call that the semi-perimeter. It's essentially half the perimeter. In fact, it is half the perimeter. Sometimes this gets messy if the perimeter is odd. But I picked one where the perimeter is even, so the semi-perimeter is nice. Okay. And now watch how I do this. This is very, 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 very particular about how I do this. I'm going to solve this equation, 18 equals W plus L, and I'm going to plug it into this equation. So this is sometimes called substitution. You probably learned this method in beginning algebra. It's where you take one equation and put it inside of the other. So my first equation says W plus L equals 18. Notice how I'm writing it in a friendly form. I'm writing it right-handed. If you want to leave it backwards, that's fine. There's nothing wrong with being lefty. But I am right-handed. I read from left to right. I write from left to right. I usually start this way and move this way, and then I go down and things like that. It's interesting. If most humans were left-handed, we would probably start over here and write this way. I don't know. I'm just speculating. But anyway. Equation number 2 is L times W equals 72. All right. So now I want to pick one of these variables. I usually pick L, but it doesn't really matter. Just pick one. Don't want to forget my order here. I'm still on this step. I'm still on the translate step. So it doesn't matter which one you pick. I picked L, and then now I'm going to plug this in where the L used to be. So that is L. L is now gone. Now you really have to make your decision and then stick with it. So if you choose L, well then L will disappear. That's called your substitute. If you choose W, it's not really going to matter. You're basically going to have the same equation. It's just the W would disappear and your equation would just have L's. It really doesn't matter. Just do it. But don't half it. Don't half pick and go, oh, I'm not sure, and then try to switch back or something like that. Just make up your mind and stick to it the whole time. Distribute, you're going to get 18W minus W squared equals 72. And that is my final translation, and now I'm ready to solve. I like to put my equations in standard order. I don't like leading negatives, so I'm going to divide everybody by -1. Last time I used completing the square. I could do that again if I really wanted to. The middle number is even. It wouldn't be hard. And if you still like that method, I encourage you to use it. But just for the rest of the folks that may find that method, distasteful, or just maybe difficult or confusing, I'll do it the old-fashioned factoring way. This is like basic math, algebra 1, W squared minus 18W plus 72. This is what I refer to as old-fashioned factoring or old-school factoring. Two numbers that multiply to be 72 but add to be 18. That would be 12 and 6. Subtract. You see how they're both negative? Two negatives multiply to be positive 72. And if you add them, you get negative 18. Now, you might not get it on your first guess. Your first guess is probably going to be 9 times 8, because that's the one you remember from 3rd or 4th grade when you were learning your times tables, right? 9 times 8 is 72. That's the one that we all remember. But there's one that we hardly ever think about, 12 times 6, yeah? 12 times 6, 72. And then now you set these equal to 0. And you solve them. I don't even need to show this step. If I have to show this step, then I need a new job. If W minus 12 equals 0, then that means W equals 12. And if W minus 6 equals 0, then that means W equals 6. So there are two possibilities. They both come out to be positive. If either one of these answers was negative, I would throw it out right now. I wouldn't even take it with me to my next step. Okay. You do need to find the length now. So the length is 18 minus W. So that means the length is 18 minus 12 or 18 minus 6, because there are two possibilities for W. But this will always happen with these problems. If the width has two possibilities, then the length has two possibilities as well. and they're typically the same thing. They are typically the same. In other words, if the width is 6 or 12, then the length is 6 or 12 also. And so to make sure that there's only one answer, what I'll do is I'll say give the width as the shorter side and give the length as the longer side. Otherwise, you're going to end up with all these different possible answers. So we're going to take the width to be the shorter side, 6, and we're going to take the length to be the longer side, 12. And I think this were centimeters, yeah? I'm such a nut for color here, so let's see, yeah, centimeters. You might have forgot. I almost did. They weren't inches this time. They were centimeters. And the only reason why I do this is because most people interpret the word longer with length and the word shorter with width. But that's actually not true. That's a speculative assumption that most of the time is the way we interpret the world, but it doesn't mean that the world is actually like that. Right? It's something that we think is true, but is really not true. Okay. I could draw a rectangle where the length is actually smaller than the width. I could do that, but I'm not going to. So I'm just going to have you throw out the width if it's longer and throw out the length if it's shorter and just keep it in that nice order. Okay, and then we can check our answer. Perimeter should be 72. So 2 times 12 plus 2 times 6 should be 72. Is that true? 24. I'm sorry, the perimeter wasn't 72. Perimeter was 36. So that's 24 plus 12 is 36. Check. Good. The area was supposed to be 72. So that's L times W is 72. L was 12. 12 times 6 was 72. Yeah, it checks. In fact, you could have just done all of this mentally just by stopping and thinking about it for a second. Does this make sense? You know? And if you have to, draw the rectangle again if you're a good visual learner. There are 3 basic learning types that you'll discover. I hope you discover what you are. And it doesn't have anything to do with just math. This is just, all of your education. Some people are very visual. They base everything on what they see. It's called visual learning. It means you put all your learning into your visual cortex. Yeah. Other folks are auditory learners. So they learn by hearing, 12 plus 6 minus 5, and you listen to the way things sound. The area is, and you memorize the sound of things. Other people are tactile learners. They memorize the way things feel. That's the toughest one because, you can't really feel these numbers, right? So tactile learners really have to find creative ways to understand what they're dealing with. With my kids when they were little, tactile learning was done with manipulatives, right? Blocks and squares and actual physical triangles, to have the kids actually hold rectangles in their hands and triangles. I'm not going to do that. In fact, I can't even get to you to hand you the rectangle. I can't hand it through the screen at you. So I'm primarily relying on auditory and visual so that you have, when I draw this bubble, some people are seeing the answer, other people are hearing the answer, and some of you might actually feel it tactilely. You can feel what a rectangle feels like. That's it for geometry. So really the only formulas you need to know the perimeter formula, and you need to know the area formula, and then I hope that you follow some type of a system. When my students come to see me, and when I used to go to school and sit in my office and wait for students to come to my office, I would often get the same questions, and they would say, Dr. Jordan, I suck at word problems. And I would say, okay, well, let's try to solve one. And most of my students that suck at word problems, they try to do this. Yeah. This is not a method. Yeah. So don't do this. This never works. Yeah. So if you've had a life of mathematical frustrations and difficulties, it's probably part of the reason could be that you're trying to read and then you're trying to solve. And your brain just goes, I'm so confused, I don't know what I'm doing. So there's a reason why I take it step by step. Notice that I don't even try solving it until, 4 steps into the process, All right, enough of me yapping about that. Let's do some physics. Next, we're going to talk about projectiles. It's called projectile motion. Okay, so the height of an object in feet, we're going to measure using the United States system. Used to be called the imperial system. We're one of the only countries that still use it, so we call it the U.S. system now. In feet is a quadratic function in terms of time. And time is given in seconds. So that's a T for time. All right. And it is always the same if you're talking about feet. It's negative 16t squared. It will always be negative 16. Again, I'm not teaching a course on physics. Otherwise, you'd have to get a whole hour-long lecture on just why that's negative 16. So I will skip the explanation, and I will just tell you, if it's measured in feet, the leading coefficient is always negative 16. Plus the initial velocity, called v sub 0 of t, plus h sub 0. Negative 16 is the gravitational constant. Again, in feet. If we translate it to meters, we get something different. So that's because everywhere on Earth, gravity is the same. Yeah. Although there are some physics experiments that kind of show that in certain areas you can affect the speed of gravity. We're not going to go there. We're not going to do some mystical, physics mathematics here, with weird things where cars roll uphill and things like that. We're not doing that. We're just assuming that everywhere you go, gravity sucks the same way, right? V0 is called the initial velocity. You don't really need to worry too much about the 0. The 0 means at time 0. So instead of saying VT0, we just say V0, indicating that the time is equal to 0. Yeah, that's how fast it's initially going. And then H0 is the initial height. And again, the subscript just means at t equals 0. In other words, blast off or launch or whatever it happens to be. Now, a projectile does not have any wings. There's no air resistance. It's a little bit idealistic, but again, most of these models are idealistic. We say, in a perfect world, we often start our sentences, well, in a perfect world, there would be no air resistance. There would be no wings so that you can't flap. There's no sustained flight or sustained energy such as an engine. Yeah. Because if you have an engine and it's actually putting out some force, then that's going to affect this formula. So this formula is literally taking an object and throwing it. Yeah, that's what a projectile is. It's basically a thrown object. Although it doesn't have to be thrown. A gun, when you shoot a bullet, that's being thrown. It's being projected by the gun. The bullet itself doesn't have a little engine in it that keeps the bullet going, right? A rocket, rockets are a little bit tricky because rockets have sustained flight, so you would have to have something more like a cannon. You can't have a true rocket like what you watch on, NASA channel, where it's like blasting off slowly. This formula would not really work for that. Although I sometimes will call something a rocket when I really just mean a cannon. Yeah. So an old-fashioned, Civil War just blasts off one time. It only gets energy one time. All right. I've gone on way too long about that. The main thing is that you are going to use this formula to model projectile motion with respect to time. Okay? So let me just write this formula up here as a little model. That's our general model. Oh no. Come on back to me. Come on back. The eraser hasn't been good for erasing, but it's been good for bringing my camera back. There we go. Suppose a rock is dropped from the top of a high cliff. Let's say 128-foot cliff. How many seconds before it hits the bottom or the ground below? How many seconds before it hits the ground below, or until it hits the ground below? Okay, so it is dropped. If you drop something, that means there is no or zero initial velocity. Yeah, you're just dropping it. So you're not throwing it, you're just dropping it. Okay. 128-foot cliff, that's the initial height. Now, I'm going to ignore the height of the person that's standing at the top of the cliff. I mean, if this were a physics class, I probably would make you do that. I don't teach physics, but my colleagues in the physics department would insist, well, there's a person standing on top of the cliff, and that person's 5'11" or 5'7" or however tall they are, and then you have to think about where they're. There's all these other things you have to include. I'm not going to do that. I just want you to get the right answer and move on and have some understanding, mathematical understanding, not a purely scientific physics understanding of how this works. All right, so I just want you to be able to put everything where it goes. So that goes there into H0. So you have your model, H of t, which we really read as the height at time t, or the height in terms of t. I'll give you the gravity for free, negative 16t squared, plus 0t, plus 128, and you can simplify this to just be negative 16t squared plus 128. The middle term is 0. And then now let's ask our question. How many seconds before it hits the ground? So that means h of t is equal to 0. Be careful, do not plug in 0. By the way, if you plug in 0, everything's going to turn to 0 except the 128, and you're just going to be right back at the top of the cliff. So t equals 0 is like the moment you're letting go of the rocket. You haven't actually dropped it yet. It's at that very second that you drop it. Okay, and then now solve this equation. You know how I like to do it. I like to make it look like a traditional equation. Set it equal to 0. Subtract 128 from both sides. Divide by negative 16. Can you do that in your head? Is it 8? I don't know. Let's see. 128 divided by 16. 8. So t squared is 8. So t is plus or minus the square root of 8, but there's no negative time. Time cannot be negative. So you can just take the ordinary square root of 8. And I'll have you round to the nearest tenth. So that would be 2.8 seconds. Almost 3 seconds. Okay, there you go. Any questions? I don't hear any questions. Oh God, at the rate I'm going, it's almost been an hour. We might have to have a part 4. I don't think I've ever had to do that this semester, but you know, Dr. Jordan likes to talk, I guess. I actually want to use this problem one more time. I guess I'll call it example 4. Suppose you drop a rock from a high cliff, and it takes 5 seconds to reach the ground. How high is the cliff? Round to the nearest foot. In other words, it's the same question, but this time I don't know how high the cliff is. And again, I got to give my physics disclaimer in case there's some students that are simultaneously taking college physics right now. There is the speed of sound here. And so the sound is going to come back, and it's going to take another extra half a second, and it's going to throw off your number by a little bit. But again, I'm not doing a physics class here. I'm just teaching some mathematics, and I'm loosely what we call idealizing the physics here to make a perfect world here. So it would be as if you heard it at the very moment it happened, which, again, sound is not like that. You do not hear it right when it happens. It takes a little while to get you. And that's how echoes happen. Anybody that's been to the Grand Canyon knows that. Or any type of big canyon, maybe Ladder Canyon out there in the East Valley out by the Salton Sea. If you haven't had a chance to go there. It's great. Hello, hello, hello. But anyway, I'm not going to get all into the physics of sound. I'm assuming that you drop the rock 5 seconds later, hit the bottom. Simple. So we already have our model. Yeah, negative 16 t squared plus 0t. Again, because it's been dropped. Anytime you drop something, its initial velocity is going to be 0. But we don't know what the high cliff is. The high cliff is our initial height, which we don't know. Okay. We do know that it hit the bottom, though, at 5 seconds. So we can plug in 5 everywhere there's a t. All right. And typically we omit the subscript, mainly because I don't want to have to write H0, 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 H0. But I mean, you certainly can, you can keep it if you like. It's up to you. It's not going to affect the answer. All right. Now hitting the bottom I'm assuming is the ground. H5 is equal to 0. We call that ground level, or level ground. We're assuming it's not going to hit, another canyon and go down even deeper, or maybe a cenote and, fall below the ground. We're assuming it's just going to hit level ground and stop. So H5 becomes 0. And I'm omitting the subscript because I don't really need it. And my variable is basically H. So now I don't have to use the square root button. So this is negative, or 16 negative times 25 negative 400 plus H. You can solve this one in your head. If negative 400 plus H is equal to 0, clearly H is equal to 400. Feet. Okay, that's dropping an object. Dropping an object. Well, what if you launch the object? What if you throw the object? It's going to be a little bit different. Yeah. Well, there's a couple things I'm going to assume now. So that's the answer. I'm done with this problem. Notice I didn't need to use the square root button this time because this is a linear equation now, so I just got 400 feet. So it takes 5 seconds for a rock to fall 400 feet. Interesting side note while I'm getting ready for the next problem. It doesn't matter how big the rock is. Yeah? Try this sometime. If you ever get out of the house, try this sometime. Drop a really big rock and then drop a really tiny rock. As a comparison, you will see very quickly, it doesn't take very long to discover that they fall exactly the same speed. It's kind of weird, yeah? An elephant falls at the same speed as a pea. Yeah, a little pea and an elephant would both fall at the same speed. Assuming the elephant doesn't have rocket jetpacks or wings or something like that. Right. Flying out Dumbo with his ears. So in this next couple examples, I'm going to throw the object. I'm tired of throwing rocks. Let's throw a ball. And all of my throws are considered upward throws. All right. So I'm not really throwing horizontally. I'm not throwing like a baseball horizontally. You're throwing directly up. All right. And again, for those of you physicists out there, the angle at which you throw it affects it, but I'm assuming that that's not happening. That you just have a little ball projector that's throwing the ball directly up. From the top of a 36-foot building, with an initial velocity of 140 feet per second. Feet per second. What is the maximum, I'll just say max height attained by the ball? And I mean height above the ground. not above the building. How many seconds until the ball hits the ground below? So there's a lot of assumptions here. It's kind of like, here's the picture. So again, read, draw, translate, solve, and check. Last time I didn't draw a picture. I guess I could have. I could have drawn a picture of somebody dropping a rock off of a cliff. But this time I think it is kind of neat to draw the picture. So here's the building. Here's the ball. Again, I'm ignoring the height of the person, and I'm assuming the ball is going to make the shape of a parabola, and I'm trying to figure out the maximum height above the ground, where the ground is down here. Okay, so that's the two questions I have. I want to know, when's it going to hit the ground and how high is it going to get? And I'm assuming that it's not going to just fall right back down and hit me in the head, or just fall right on top of the building. So here's the building. All right, whatever. Okay. You don't really use the picture to solve the problem. You just use the picture to help you translate into an equation, or to help you get an understanding of what it is you're trying to do. So again, we have the same height function, 16t squared, negative 16t squared. The initial velocity, that's your v0. Make sure you include the variable on that one. So it always goes second power, then first power, and then constant. That's your h0. Okay. So maximum height of the ball. What's the maximum height? That's called the vertex. So I'm going to teach you a trick that I'm not sure if this made it into my other two lessons. If it didn't make it, I'm actually glad, because it's probably better that you didn't know this trick back then. If you're just getting caught up, you know, maybe you're a little behind in your homework and now you got the trick. I guess you could go back and use this trick to help you with some of the other problems. I'm laughing because you're going to be like, why didn't you tell us this, a week ago, or 2 weeks ago, or something like that? I didn't tell you because I didn't want you to know it back then. If you went to a tutor, they probably told you. This is what I call the quick vertex. All right, it gives you the x coordinate only. So it doesn't give you the entire thing. Yeah. Or in this example, the t coordinate. X or t coordinate only. It does not give you the y value. All right, so x, or in this case t, is negative b over 2a. So here's your a, and here's your b. And so to find the quick vertex, at least the x part of it, you can use this recipe. I only use this for word problems because on the other problems, I don't think it's as useful. But on word problems, look at this. You would not want to be using the quadratic formula or completing the square or anything like that. I mean, you could if you wanted to, but I think the quick vertex works nicely. So negative 140 over 2 times negative 16. So that's negative 140 divided by negative 32, which is 4.375 seconds. Okay. Now, that is not the maximum height. That is the time that it takes. So So now you have to plug in 4.375. I would not round it yet. Don't round it yet. Plug it in to find the height. So you're going to get negative 16 times 4.375 squared plus 140 times 4.375 plus 36. All right, so you got h of 4.375. Definitely going to want a calculator for this, so square it. Multiply it by 16, negative 16, so you're going to get negative 306.25. Now do this one, 140 times 4.375 is 612.5, and then plus 36. So I got negative 306.25 plus 612.5. That just becomes positive. You might notice that these guys are always half of each other. I don't know if that's always true, but they are in this case. That's double of that. Yeah, so it's just going to go back to that. Plus 36. Oh, I screwed up. I hit times. So I'm going to clear it out. 306.25 plus 36. I probably could have just done that in my head. 342.25 feet. I'm just going to round to the nearest foot. So, unless told otherwise, 342 feet above the ground. This is the number of seconds. This is the number of feet. Okay. So check, we got that. After 4.375 seconds, it's 342 feet above the ground. And then what happens? It starts turning around and heading towards the ground. My next question is, when does it actually hit the ground? The ball hits the ground when h of t is equal to 0. In other words, y. Yeah, this is like the y and this is like the x. Yeah, if you like to use y and x, I would never know. I mean, you could read the question on the computer and go, you know what, I'm just going to use x and y because that's what I've been doing since I was like in high school. It's the same math that it was in high school. I mean, it's college level, so there's more vocabulary, there's harder problems, my expectations are higher. But math is math, folks. I mean, it hasn't changed, you know, and it's not gonna change. You're changing, but it's not changing, right? So I want to know when the ball hits the ground, so let's go ahead and do our formula. H of t is negative 16t squared plus 140t plus 36, and we're going to set this equal to 0. So you got a couple ways to solve this. One thing I like to do is look for a common factor. Looks like everybody's divisible by 4. That's about as good as it gets. I think. Is 140 divisible by 4? I think so. 35, yeah. So just to make things easier, try to pull out the greatest common factor, the GCF, and always take out the negative as well. This is really just a suggestion. It's not a law. You don't have to do this if you don't want to. You could just go right to solving this equation if you want. That's called the brute force method, a stubborn method, right? I'm just going to do it, I'm not taking your advice. I'm just going to do it my way. But if you factor out the negative 4, Then when you do the quadratic formula, which I'm going to do the quadratic formula to find the ground, rarely ever is the middle term even. I know it was even originally, but it's not going to be even now. If I divide this by 4, it's definitely not going to be even. So the chances of completing the square being a good technique are very, very low. And then the other thing is it's rarely ever factorable. These things, I mean, you're talking about the real world. You're going to go out there and throw a ball off a roof of a building and hope that the result comes out to be factorable? I mean, come on. I mean, we're not living in that perfect of a world, right? Even math, we can't idealize that much. So the point I'm trying to make is just use the quadratic formula for these. Just set it equal to 0. What I'm going to do is divide both sides by -4 first. 0 divided by -4 just becomes 0. And I'm going to use the quadratic formula. So negative blank plus or minus the square root of blank squared minus 4 blank blank all over 2 blank. Have I mentioned this before? I feel like I have. I don't put A, B, and C in there because they just get in the way. The letters are in the way of the solution. So I strip out all the letters and I put parentheses all over. Negative B, that's B, so 35. Now you can read it yourself. B squared, 35 squared. 4AC, so 4 times 4 times -9, AC. And then 2A, 2 times 4. So I'm going to get -35 I'm just going to come up here because I already know I'm not going to have enough room. So it's -35 plus or minus the square root of 35 times 35. I'm using my old, bill calculator. I use this one to do my bills. Negative is a positive. 4 times 4 is 16 times 9 is 144. So plus 1225 equals 1369 over 8. Okay. And then remember, time can't be negative. So since time can't be negative, we omit the negative radical, or the negative root, I'll call it. All right. Now, sometimes people mishear me. They hear me say, oh, Dr. Jordan said get rid of the negatives. I don't mean that you can't have a negative number in the mix. There's definitely a negative number in the mix. Some people panic and they go, oh, no, I can't have a negative. Dr. Jordan said I can't have a negative. No, I mean that the overall answer can't be negative. So by omitting the negative root, that's going to guarantee that I end up with a positive. Oh, nice. Look at that. You want to see that on camera? 1369. I hit the square root button, and it comes out to be exactly 37. That's beautiful. Divided by 8. That's a beautiful perfect square, 1369. Now you should memorize that. It could be the life of your Thanksgiving party. The square root of 1,369 is 37. With these types of word problems, I like decimals, so that's seconds. That doesn't seem to make much sense. Huh. Hmm. Hmm. Oh my God. Oh my goodness. Look what I did. Rookie maneuver. Rookie maneuver. I need to go back to the farm team. Look at that. The 35 is positive. Oops. Correction. You know what, though? This is actually a good teachable moment. When I got 0.25 seconds, I mean, that doesn't make sense. We already said that it takes like 3 or 4 seconds to get to its highest point. How can it hit the ground before it's even got to its highest point? What happens is the negative 35 was supposed to be double negative. Let me make that even more clear. Negative 35 with a double negative, so the 35 should have been positive. And there I was making a big speech about how it would be okay if that term was negative. Well, it would have been okay. That's not what made the problem, but I mean, that would have been okay if it was true, but I mean, it's just simply not true. So in this case, it's okay. Now again, notice I didn't change that to a positive. I went back here and I corrected my answer before somebody sends me an email. So if you're already sending me that email, you might as well delete it now because I found it. Now this makes a lot more sense. 72 divided by 8, which is 9 seconds. I probably would have caught that when I got to the last step, which is to check my answer, but I'm trying to encourage you to check as you go along. And so a quarter of a second, 0.25 just did not make any sense. So that's the correct answer, check. And I'll actually just call that my check now. So I have now checked my answer by using common sense, by finding my mistake. All right, so let's lesson learned. Be careful. Yeah. When you use the quadratic formula and you do negative b, well, negative b is the negative of the middle term, and so that's now positive. Okay, I'm going to try the last example, hopefully without making any mistakes. NASA launches a test rocket. And again, I'm going to put the word rocket in quotes. So this is a launch that just, boom, it just kind of blasts off and from a height of 15 meters. Above sea level. So maybe they're down in Florida somewhere. Their launch pad is 15 meters above sea level. Okay, so here's the sea level. Here's the launch pad. This is 15 meters. And then you got your rocket. All right, and the rocket's going to blast off and then land in the ocean. Okay. And again, it's a little bit unrealistic because a rocket goes, I mean, it has a constant flow of energy. This is more like a cannon. It's like, boom. It would be like a 19th century rocket. Read the book Round the Moon, yeah, by, who's that author? It'll come to me before the lesson's over. Okay. How many What is the maximum height attained by the rocket? I'll just call that max height. And how many seconds or how long before it hits splashes? We call that how long until splashdown. We call that splashdown. Splashdown. You can tell I'm a child of the 70s, back when the rockets used to splash into the ocean. They got some pretty fancy ones now that will actually land back on the launch pad if you've been watching the television in the last couple of years. But this is the 1970s version of the problem. In fact, mixed with a little bit of the 1800s, when the rockets would be more like a cannon. Yeah. So a more realistic thing would be like this. It's like a cannonball. That's the kind of rocket we're talking about. All right, it doesn't have an engine. Just pow. All right. So these are the classic questions that I typically ask. You know, where's the maximum height? Because I want you to know how to find the vertex, and when is it going to hit the water or the ground or whatever it happens to be. I will give you a hint on this one. 16 feet is 4.9 meters. I don't expect you to know the metric system unless you're taking my beginning class. It's actually pre-algebra, where I make my students learn the metric system. If you are a former student from one of my previous classes, maybe you already know this conversion, but I'm just going to give it to you for free. 16 feet is 4.9 meters. So this is the way the rest of the world does math. We here in the United States are strange and a little bit slow, right? A little bit behind the rest of the world. We're catching up. Hopefully on November 3rd, you'll all go out there and vote. Oh, I'm not supposed to say that. Well, yes, I can say that. Go vote. Yeah. Help make this world a better place. We can start catching up with the rest of the world, maybe, if things turn around. Okay, so 4.9 becomes our leading coefficient. T squared. Oh, shoot. I was talking too much and I left out something. Initial velocity is 166. Where could I squeeze that in? Right here. Initial velocity, 166 meters per second. m/second. And then I'm still asking the same two questions. What is max height? And then how long until, or before splashdown, until splashdown. All right, almost blew it. I just didn't read the question all the way. So remember, the first letter in R is, the first letter is read. Draw, translate, solve, and check. So I was reading it, I was drawing it, and you frequently go back and forth between reading and drawing. Now I'm translating it into a function, 166t plus the initial height of the launch pad is 15 meters. The quick vertex, this time it'll be negative 166 over 2 times negative 4.9. What's that? 166 divided by 9.8. They're both negative, so that's going to be about 16.9387. Let's just say 16.9 seconds. Tenth of a second is fine. When you do this, I've actually preset the homework problems to have a tolerance, so you can be close to the right answer and get it right. But I recommend reading it carefully, rounding it, and if you really are are concerned, then just don't round it. Keep all the decimals that are on the screen. I think it goes 7, 7, 5, 5, 1 or something. It certainly wouldn't hurt to keep all the decimals. It wouldn't affect the final answer very much, just how much work you have to do. Now again, this is not the height. This is not the height. This is the number of seconds. So you have to go back to here and plug in this value. That's the reason why I'm only going to use 16.9, because I don't feel like plugging in all of those decimals, and I know that they're not going to affect the overall answer very much. $16.9 times 16.9. And then I'm going to square that first and then multiply by 4.9. And I'm going to get negative 1399.489. 16.9 times 166. 2805.4 plus 15. Now I'm going to subtract 1399.489. I get 1405.911. I wouldn't be surprised if I've made a mistake because I'm going so fast. Again, I'm late to my office hours. All right, and then you can round to the nearest foot. 0.9, I'm just going to round up. So it's going to be 1,421 feet above sea level. It's about a third of a mile. Not quite. No, it's about a quarter of a mile. A little more than a quarter of a mile. Oh, shoot. No, it's not. It's meters. Yeah, so it's almost a mile. Yeah. Like 1,600 is a mile, right? 5,280 times... yeah, I don't know. I'm not doing the metric system today, though. So 1,421 meters above sea level. Oh, goodness. I don't know why I even asked. How long until splashdown? This one's not going to be very fun. Well, it might be fun if you're into this kind of thing, but when you do the metric system, I mean, I guess this would be one argument for sticking with the American way. The metric system always has these decimals, which means you're not going to be able to factor it, which means you're going to have to do the quadratic formula. Now, this time my b is not negative. My b is 166. So I'm not going to screw this one up. Plus or minus the square root of 166 squared minus 4 times negative 4.9 times 15. Negative 4.9. Now this one's kind of weird. I'm actually going to keep both answers and then decide when I'm done which one is negative, which one's positive, because it's kind of hard to tell. Right? It's hard to tell which one's going to be negative and which one's going to be positive. So 166 plus or minus the square root of 166 squared. So that's 27,556. Negative is positive. Times 4.9 times 15, 294, all over negative 9.8. We already know the answer to the first question. It's 1,421 meters. Now the second question, we got negative 166 plus or minus the square root. 27,556, 27,850 divided by negative 9.8. Now the chances of this being perfect are so slim, I'm not even going to hope Just going to do it. Nope. It's a decimal. 166.8831. Blah, 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 blah. Over negative 9.8. So it's hard to tell which one of these. And by the way, let's just do one decimal place here. That's all we really need. Or we could round up to 0.9. I rounded up. Okay. Now watch. I'm going to keep both because one of them's negative, one of them's positive, but right now I can't tell which. So let's do both of them. 166 plus negative 166 plus 166 over negative 9.8. Or the other one is negative 166 minus 166.9 over negative 9.8. So this one is 0.9 divided by negative 9.8. This is the negative one. This one is the positive one. Negative 332.9 divided by negative 9.8. So the one that you think might be negative, look, it's got 3 negatives, but when you simplify it, it becomes a negative divided by a negative, which becomes a positive. So about 34 seconds. Or you could round, yeah, so this 6 rounds the 9 to a 0, so it's 34.0 seconds. I typically like to round to the nearest tenth of a second. That's a weird one. Whenever the number next to the tenths is bigger than 5, and then if the tenths value is a 9, then it rounds to a 10, which rounds the 3 to a 4, and then it's 34.0. Again, that's the kind of thing where there's a tolerance. If you're off by a little bit, it'll still mark it right. All right, that was a heck of a lecture, huh? I hope you're not all too confused. Unfortunately, I did not get through all the applications. Notice I haven't done any money problems yet. So until we meet again in part 4, this is Dr. Jordan. I will see you on the internet. Stop.